Thank you. So yeah, I'm going to be discussing FeUdal networks for hierarchical reinforcement learning. So first off, why do we care about hierarchical reinforcement learning? So the reason is reinforcement learning is hard. When we have long time horizons and sparse rewards, it's really difficult to make our models learn something correct. And the idea is that if we kind of use some methods that are based more on the way humans make decisions, maybe we can improve the reinforcement learning methods. Ooh. So first we'll discuss hierarchies. So if we think about the way people make decisions, how do we think about, say, if we're hungry, what do we want to do? If we're hungry, do we think about, oh, I need to move my leg 2 centimeters this way and then activate this muscle slightly? No, we think, I want to go to the fridge or I want to go to a restaurant. How do I do that? I get up and I walk. We don't think at this fine-grained level at all the time. Or the same way if we're learning something. If we want to play an instrument, we don't randomly move our fingers until it happens that we play a good song. We have different levels of abstraction for how we think about these decisions. And another kind of motivation is that hierarchies tend to work in machine learning quite well. So another kind of form of hierarchy is we learn hierarchical features commonly. And well, even in CNNs that we use for reinforcement learning. So hierarchical structures just seem intuitively appealing. So the next part is FeUdalism. So this is FeUdal hierarchical networks. If you're not familiar with feudalism, it was a questionable system in Europe in the Middle Ages. So basically, we have this extremely hierarchical system where if you're at the bottom, you're a serf, you have no power, and you just have to work. If you're at the king, you have all the power, and you can tell other people what to do. And there was also different kind of levels in this hierarchy. And the whole idea was basically people have a lot of control over the people below them. And so that's why they used this name. So the first thing I'll mention is FeUdal reinforcement learning. This was a paper by Geoffrey Hinton, and I can't remember the other author. But back in 1993, they first suggested this method. And this basically is it's a hierarchical method where the key aspect is that in the hierarchy you have a layer of agents, and each agent can only interact with an agent right above or right below it. So there's kind of, you can have a stack of these as big as you want, but the kind of key thing is the bottom level agent will actually take actions in the environment, and the top level agent will actually get rewards from the environment. So you can think of it like the king takes the real reward from the environment, and then the king decides how much reward is given to the agent below. So that's the basic idea of FeUdal reinforcement learning. So yeah, it's based around reward hiding, which is that idea that managers have absolute control over the reward that goes to a lower agent, and information hiding, which means that you observe the world at different resolutions. So managers don't know what's going on at other levels of the hierarchy. And FeUdal reinforcement learning was limited. Their experiment was just a maze task. So they used Q-learning. They solved the simple maze task. And it was kind of this this problem that really easily lent itself to a hierarchical task. So it worked here, but for a long time, there wasn't a whole lot of interest in FeUdal reinforcement learning. So then we fast forward to 2017, and we have FeUdal networks. So this is actually a simplification of the FeUdal reinforcement learning idea. So in this case, we only have 2 agents. We have a manager, and we have a worker. So what the manager does is decide the goal for the worker. The manager also receives rewards from the environment. So the worker's goals are entirely dependent, the worker's rewards are entirely dependent on the goals set by the manager. The worker does not receive rewards from the environment, at least in the idealized case. The worker does take actions in the environment, though. So the idea is that the manager acts at this abstract level, and it tells the worker what to do. And the worker takes these fine-grained actions in the environment and then achieves rewards from the manager for doing that. So just a quick idea of the architecture. So we use a common embedding state for both of these things, for both the worker and the manager. They both use RNNs. And the goals produced are actually directional rather than absolute. I'll get into this in detail later. And we use it, and we train it using a transition policy gradient for the manager. Okay, so that last diagram I showed was a really simplified version. Here's the true architecture. So if you see, we have the manager, we have the worker, and now we'll get into some details about what's actually going on inside this. So the first thing to notice is that there's a shared dense embedding for both the manager and the worker. So the idea is we take in some input, like a video game, and we have to compress this into a smaller representation. And so we feed the exact same representation to both the worker and the manager. They use a CNN. I think it's very similar to the one they used for like the original DQ and Atari paper. Nothing too fancy. So the next thing is if we look at the manager, so what does the manager have to do? It has to produce a goal. So how are we going to produce this goal? The idea is that we use an LSTM on this embedding. We actually compress the embedding once more and then use an LSTM to generate a goal. So this is the goal that we're going to use for the worker. We generate this goal in a low-dimensional state space, or a low-dimensional space, so it's not actually a goal in the environment. And this is trained using transition policy gradient, which I'll get into details later. So the basic idea is that the manager observes the environment and generates a goal, and this goal is a directional goal, which is used to train the worker, or which is how we reward the worker. So moving along to the worker. The worker actually embeds, so the worker uses an LSTM, and what this does is they create an action embedding. So you get this matrix where the rows represent the actions and the columns represent an embedding dimension. So when we have this action embedding, we can also create a goal embedding. So the manager gives the worker a goal. And then what the worker does is it compresses this goal again down to something of dimension k using a linear transformation with no bias. So once they do this, they kind of have these two matrices that line up, and you can just take the dot product of the two of them, and you can output your action. So the idea with this, this wasn't totally explained, but the idea is you have a linear transformation with no bias, and the idea is that it's not possible for this thing to just, it's not possible for the worker to totally ignore this thing, because the way we dot product it with this, yeah, you can't ignore the input. So yeah, so the action, if we look, just kind of reiterating what I just said, we just multiply the goal embedding with the action embedding, and this produces an action. We can take the softmax of this and get our distribution over actions for the worker. Okay, so now along to the interesting part. So we have our manager, and the manager produces goals for the worker. So normally we would think about training something. We think about training an agent to produce good actions. In this case, we don't produce good actions. We try to produce good goals. And they're actually not absolute goals, so we don't specify a location. What we do is we specify a direction that we want the agent to move in. So this is, they train it using actor-critic. So, and that's what this equation shows. So if we look at the A, so this is the advantage, normal kind of advantage function. And then if we look here, we have cosine similarity. So what this is saying is basically instead of trying to select good actions, what we're doing here is we're trying to make the direction good. So we want to output goals that are in a good direction as far as reward is concerned. So that's the whole idea of the transition policy gradient. So how is the worker trained? So in the normal case, right, we have an agent that gets a reward from the environment. But here, we don't get a reward from the environment. Well, we don't get an intrinsic reward from the environment. The reward for the worker is entirely from the manager. And so the manager's goal is shown right here. So in this case, we want to take the reward as how is the agent going in the right direction. So if the agent is going in the same direction specified by the manager, the goal will be high. And if not, the goal will be low. So training the worker is also done using an actor-critic. It's done using more standard architecture, or more standard actor-critic, I should say. Because in this case, we actually do have a normal kind of reward. It just happens to be in the form of the distance rather than from the environment. And some kind of unfortunate thing to see is that this reward that they actually use is not really hierarchical. So ideally, we would think that, oh, we just get the reward exclusively from the manager. But what they found was that they get better performance if they use a weighted sum of the environment reward and the manager reward. So they just ended up using this. So it's not truly hierarchical, but it's kind of close. And they did some experiments to show that basically the intrinsic reward does work. So this was just something that ended up performing better, was to use the external reward as well. So one key contribution of this paper is directional goals. So what was their explanation for why directional goals are good rather than absolute goals? So the idea is, well, some of their explanations were that it's feasible, so it's kind of possible to move in a direction in any situation. It's kind of, they said it was easier, maybe if you have a farther away goal. It's easier to just pick a direction to move in. And as well, structural generalization. So their idea was that goals are more meaningful if you think about a direction to move in rather than an absolute value of like location you want to go to. So another key aspect of this was a dilated LS TM. They didn't give a whole lot of information about this. So this is what was used to train the manager, or this is used as the manager, I should say. So the idea is that they need to preserve rewards over long time periods. So they use this dilated LS TM architecture. I took this diagram from a dilated RNN architecture. This is basically, the LS TM is a specific type of this. So you can kind of think of the dilated LS TM as similarly, right, where we just have these skip connections instead of kind of the fully connected. So we could see here in this case we have the kind of regular connections, but here we have like dilation of 2, or here we have dilation of 4. So they found that this gives good results, so that's what they used. And as well, the manager works at a lower temporal frequency. So they sum the outputs over the previous 10 steps. So that's another kind of key thing. So on to the results. In Atari, it's kind of hard to see, but basically some things, the FeUdal, the fun is the FeUdal network. In some cases, the FeUdal network performs better, and in other cases, it performs worse than the baseline, which was a CNN LS TM. And their idea, which I didn't really look into detail, but they said that whenever you have more longer-term planning, the FeUdal network performs better, which is intuitively what we would hope so, because that's the goal of the FeUdal network. But at the same time, didn't really go into details about why, these particular games. Like, there wasn't much discussion of, say, why Enduro is a longer-term reward. But we can just take that as is. Another interesting experiment they did was the water maze. So if we look here, we see some episodes. This isn't too interesting. What's interesting is here, if we look at these different colors represent different sub-policies. So what this shows is that the agent actually learns meaningful sub-policies. So it learns one sub-policy to circle around at kind of a great radius, and then different other ones depending on their radius. So in this game, I should have mentioned this, the goal is to find a platform. So your agent is dropped somewhere in this, and it has to navigate to a platform. And so over episodes, we keep the same platform, but the agent gets dropped in different locations and needs to learn to find it. So the idea here is that we see that there's meaningful sub-goals being learned by the FeUdal network. They're not necessarily the best sub-goals. There's nothing that says that going around in a circle like this is an ideal thing to do, but nevertheless, it does demonstrate that some kind of meaningful sub-goals are being learned. So this temporal resolution ablation. What they did here was just to prove that their network, that using a lower temporal resolution for the manager is actually useful. So if we look here, the blue line is the FeUdal network. The green one is no dilation, which really destroys it. As well, if we look at a time horizon of 1 rather than 10, it'll reduce the performance consistently. So this is just kind of proving that what they did wasn't just random tweaks. And then here we have intrinsic reward ablations. So what this is proving that the intrinsic reward is actually useful. The idea was they took the weighting they used for the intrinsic reward, and varied this. So if we see here on the rightmost, we see that with full intrinsic reward, agents still perform quite well. They perform consistently quite a bit worse with no intrinsic reward. So the idea with this is just, it's a really good thing to show that the intrinsic reward actually is useful, and it wasn't just some hacky motivation thing they did. So yeah, the intrinsic motivation is really useful, even though they added the external reward as well. So another kind of main goal of hierarchical reinforcement learning is the idea of transferring. So we think that if we have this hierarchy of policies, it should be easier to transfer it to new task. And this is what they did here. So they changed the number of action repeats done playing Atari games. And they found that basically the FeUdal network performs much better than other networks if you're using transfer learning for this. And again, the idea is that this is because the manager's policy does not depend on how the worker actually takes these actions. The manager outputs a good direction, and then the worker just has to figure it out. So it's almost like it's easier to transfer because half of your network doesn't need to be retrained. So in summary, they used directional goals. This was quite useful. They used a dilated LS TM, which according to their results is crucial for their high performance. In some of their studies, they showed that they improve long-term credit assignment. They also improve transfer learning in the Atari games. And their studies also showed that these goals are meaningful low-level behaviors. They weren't just some hacky thing that happened to work. It does seem that these correspond to reasonable low-level policies. So Okay, yeah, just a few thoughts. I thought it was really good that they used these ablation studies, whatever they're called, just because a lot of the time people just hack a bunch of stuff together and you have no idea what created the benefit. I think that this kind of really enlightens to show, like, say the intrinsic reward is really useful, or to say the dilated LS TM actually improves performance. Another thing was their action and goal embedding was a little bit strange. Normally, if I were to like just think of what you should do on this problem, you would think just feed the two things into a fully connected network and see what happens. So they kind of gave some motivation about making sure it doesn't ignore the intrinsic reward. But anyway, I was just kind of left a little bit confused about that. And that's it. Does anyone have any questions?